applause, please, to Stefanie. Thank you.
All right. Thank you, everyone, for coming and tearing yourselves away from the break. So I'm going to talk about a personal project of mine called Data Morph and why you have to be careful with using summary statistics. And my clicker's not working. Okay. So a little bit about me before we dive in. So I'm a software engineer at Bloomberg in New York City, and I'm one of the founding members of Bloomberg's data science community. I'm also the author of a book called Hands-on Data Analysis with Pandas, which if you've been to a couple of past editions of PyCon Portugal, you've probably seen floating around. I'm going to skip over the other two just in the interest of time. So let's talk about first why summary statistics aren't enough to describe your data. So if we look at these three data sets, right, we all agree that they're different. Very obviously different, right? But if we were to have looked at the summary statistics, so the mean in X and Y, the standard deviation in X and Y, and the correlation coefficient, particularly the Pearson correlation coefficient, they're exactly the same, right? So if we had just looked at the numbers, it could have been any one of these or an infinite number of other ways those points could have been arranged, right? So it's clear that that tells us nothing. So one thing we could do to potentially start differentiating between those numerically is to look at what are called moments. So you actually are already familiar with a couple of statistical moments. The first moment is the mean of the distribution, which we already saw was the same. The second moment is the variance, which again you will see here is the same in X and Y. That's because we saw the standard deviation was the same. In this particular case, once we get to the third moment, we now start to see differences. But it's sometimes possible that you need to go third, fourth, fifth, sixth, seventh, and so on to actually start to see differences numerically in the data. So to understand what this third moment and fourth moment, and I'll stop there, are, I've added histograms here. So we can see the marginal distributions of X and Y. So the third moment is actually called the skewness, which you may have heard. The distribution perhaps has left skew, negative skew. And there's an example of that over here. So you see here, the Y skew is very highly negative, and that is shown here that there's a shift negative here to the left of the distribution. So that's a measure of the asymmetry compared to the standard normal. Now, the other metric I'm showing up here is kurtosis. So that's the fourth moment. And that's a measure of the weight in the tails of the distribution, so the ends, compared to, again, the standard normal. So when we started looking at the moments, you'll notice that everything was now X and then Y, and we don't have any measure of how X and Y move together. And that's typically where you would reach for a correlation coefficient. Now, the problem here is that typically when you ask a library for correlation coefficient, you get the Pearson correlation coefficient. And that is a measure of linear correlation between variables. So here, it's innocuous. This is saying that there's no correlation. So we're not going to draw any dangerous assumptions. But if we look at this data set, this is a famous data set called Anscombe's quartet. And this was made in 1973 and is still pretty much the standard that you see used in examples to explain this. And in this case, the Pearson correlation coefficient is indicating that there's a strong positive linear correlation in all of these data sets, right? I said linear correlation. This is not linear, and neither is this, right? And yet those are showing strong positive linear correlations. So you cannot just rely on any of those numbers, right? You have to use this in context with the visualization. So I want to tell you about an interesting paper called A Hypothesis is a Liability. This is from 2020. And the researchers argued that simply approaching a data set with a hypothesis can actually limit the thoroughness to which the data set is explored. And I want to walk through the experiment that they did. So they took students in a statistical data analysis course, and they split them into two groups. They gave both groups the exact same data set. In one group, the students were just told to explore the data set, report back on their findings. In the other group, they were given the task of testing these three hypotheses you see up here. Notice that each of the hypotheses is dealing with one of those summary statistics we just saw: mean, correlation coefficient, correlation coefficient. This was the data, right? So it turned out that the students who were told to look at those particular hypotheses, we're 5 times less likely to realize that the data set was actually just fake data in the shape of a gorilla. Right? So just going in with that preconceived notion of, I want to do this task, I want to look at summary statistics, blinded them to what was actually going on in the data. So how do we encourage not just students, but also practitioners alike to be more thorough in their analyses, to hopefully not fall victim to something like that? I'm not saying it won't happen, it will continuously happen, but to make it less likely and hopefully more of a cautionary tale to avoid that. So one thing potentially is that we can make more memorable teaching aids. And in 2017, researchers at Autodesk did just that. So what they did is they expanded on the idea of the Anscombe's quartet, which we saw earlier. And they started with this drawing up here of a dinosaur called the Datasaurus, which they captured the same summary statistics before. And this time, instead of manually drawing them, because that would have been a lot more challenging than Anscombe's quartet, where there's just only, I think, 10 points, here they use an algorithm to turn this shape into all of that. So the same number of points, they're just moved around into different shapes. And they share, again, the exact same summary statistics. And particularly important for this work was that instead of just showing those static images, they also created animations. So now you can appreciate that it's not just the dinosaur and the circle that had those same summary statistics, right? It's every single arrangement of points that we get in between. So going from the dinosaur to the circle. And also, I'm going to tell you about the algorithm in a little bit, but it's randomly moving points, right? So now you have to also appreciate that there's an infinite number of ways that this transformation can happen. So those summary statistics just looked at in isolation tell you absolutely nothing about what this data looks like. And then I noticed a new problem that came from this. So I noticed several posts on LinkedIn where someone would maybe share the Anscombe's quartet, and someone else would chime in, oh yeah, there's this other special data set of this dinosaur that also does this. So people were attributing there being something special about the way points are constructed that allows this to happen. And that's not at all the case. This can be done with any arrangement of points. And so this was part of the reason which gave me the idea to create Datamorph, which I'm going to share you about right now. So Datamorph I see as an educational tool. So I just want to preface it with that. You're not going to be using it in your analyses, but it's more to showcase this principle in a more memorable way. So I hacked on top of a research code base and turned it into a Python package that's actually installable and usable by people like students. You still get those animated results, but now it's possible to use additional data set because things are no longer hard-coded. So instead of only being able to use the dinosaur or Anscombe's quartet, you can now use a data set that you generate with X's and Y's in the shape that you desire. And there's also additional built-in data sets that I will show later. Right, so now this means that people can experiment, right? So people can use this in a class. They can create new data sets or they can create new shapes and just play around with how this works and hopefully convince themselves more that, yes, I absolutely need to be visualizing my data always. It's not optional. Right, and now it's no longer limited to those discussions on LinkedIn that there's this special dinosaur and then there's Anscombe's quartet, right? People can share other images, it's anything. And I think it's still happening because now I've seen people that add to that conversation and share one of the examples that I will show from my project, and then they stop there. But you know, we're getting there. There's now at least 3 in that conversation, whereas there was 2 or 1 before. So this is Datamorph. So as you can see, I'm converting the Python logo into a heart shape. And this obviously was not in the original research, right? So this is, again, proof. This works for anything, right? The Python logo is an SVG, you extract the points, and then you can run this algorithm on it. So the whole time, the summary statistics are preserved to 2 decimal points. You can actually extend that out further. And you can, I'm working on now adding like the median. So you can constrain this further, right? You're just constraining the optimization. So it does become a little more, it takes more time, but this principle applies to more than just these summary statistics here. So if you wanted to run that on your computers, it would just be as simple as this. You install the package, and then you can run on the command line that you want to use these built-in shapes. So under the hood, it looks like this at a high level in Python. And I'm going to walk through how this actually works at a high level and the changes that I made to the research to make this possible. So the first thing is that in the initial research, there was no concept of a data set that I'm going to show you here. They was basically just, here's a set in X and Y's and a data frame, and then that's it. And that works, yes, but it's not possible with just that information to easily extend it to work for arbitrary data sets, because then you have to hard code everything, and that's how the initial research was. So with data morph, there's a data loader class, and then you can specify that you want to load a built-in data set, which I have up here, or you can use your own data set. So for now, CSVs, but I wanted to support something in the future where perhaps you give it a PNG and the pixels are extracted and sampled and then turned into something like this. So this is a data set in data morph, right? So again, to remove those hard-coded values, extra logic needs to happen. And so what I came up with was a system of bounds. So you can see the data set we saw before in the middle, that's just a set of points. And then we have 3 sets of bounds. So this innermost bound are the data bounds. It's the tightest bounding box that you can fit around the data. So it's basically the extent of it in either direction. Then this middle bounds here are the morph bounds. That tells the algorithm how far it's allowed to push the points outward before it can't go any further so that they don't drift too far away. And then the final bound here is for plotting. So it allows for a constant frame of reference when sampling frames to put in an animation. So in the current release, these are the shapes that are available. You'll recognize the gorilla. That was something that came recently. I had people working on it, I think, starting in a EuroPython sprint, and then some other people took it over. But you'll see that several things here have come from sprints at Python events over the last year or so. But yeah, so these are the built-in ones, but you can also use your own. So once we have the data set, so that's our starting point for the transformation, we then can calculate the shape, which is going to be the ending point. So we saw that the Python logo was the data set we started with, and we're going to the heart. So we use the shape factory. We tell it we're going to be morphing from this data set, and then we're going to go to the heart, and then the heart can be calculated. So in the original code, there was no concept of shapes. It was just a giant if-else, and it was basically just giving numbers for formulas each time, like a lookup table. You're starting from the dinosaur, you're going to a circle, so here are the points, and this is the formula, right? But that really didn't make any sense to me. The algorithm does not need to know how shapes work at all. All it needs is a distance, right? So I abstracted all that into shapes, and so in order to make this work for arbitrary input, you have to define heuristics and rules for how you place a shape in the XY plane. So in the top row, I'm using the Python logo data set, and in this row, I'm using the music data set. So the Python logo is symmetric, so it's the same range in X and Y, but the music one is taller than it is Y, right? So you can notice that the heart doesn't get stretched out, but it's still in both cases centered on the points and appropriately sized. And you'll notice also, like for example here, the slope is different slope of these lines, right? So you can tell that these shapes are using the data itself to determine where to be placed. And you want to do that because then that optimizes the chances that the points actually end up on the shape instead of failing to go there. So here are all the shapes that are available. There's significantly more than the original research, and several of these did come from, again, sprints at Python events. So a little bit about how the shapes actually work. So I mentioned before, initially there was that original if-else, which was basically just capturing the distance logic. So when you think about what a shape needs to do, you need to be able to do 2 things. You need to be able to say, give it a point, and it needs to tell you how far away that point is from it. And then the other thing is just for visualization. You want to be able to plot that shape. This is mostly for the docs, but it's also like a sanity check as you're creating the shape. Does this look correct? So I made a base class of the shape that does just that. It defines what it means for something to be a shape. And then I'll just highlight these 2 here. These are other base classes. So there's line collection and point collection, which are appropriately collections of lines or points. And what's nice about these is that the line collection defines the distance metric. So the minimum distance to any of the lines is the distance to any line collection shape. And likewise for the points. And that means if someone wants to create a new shape that's a collection of lines or a collection of points, they don't even need to figure out how to calculate the distance. It's already done for them, right? All they have to do is define how the shape gets placed in the XY plane based on the input data. And that involves quite a bit of math. Usually when you do them, you see that some of these are, well, several of these are trigonometric equations that you have to figure out. This one, even the heart, this one, is actually a trigonometric equation. And I remember when I was figuring that out, there's like a page, I think, in Wolfram Alpha or something. There's at least 20 different trigonometric equations for different styles of hearts that you can pick. So it's a fun thing to look at if you're just curious. But yeah, it's a bit of like mental gymnastics and math to kind of figure those out, and they're fun little puzzles. And again, that's where this can become something used in education, right? So not just about doing the transformation, but how do you actually figure out how to place something in space using equations so that it works for multiple different inputs. And so once we have that data set and the target shape, then we have everything we need to do the transformation. And then we can use the data morpher to actually perform the morphing on that input. And you notice here we have a specification of how many decimal points we want to hold those statistics to. Okay, so as I promised before, I'm going to tell you now how the actual algorithm works. And this part is pretty much the only part that is largely untouched from the initial research. And so here's the opportunity where if someone wants to contribute something, a brand new algorithm would be awesome. So just plugging that in. So the algorithm that it's currently using is called simulated annealing. So it's a randomized optimization algorithm. So a point is picked at random, and that's when you see it in blue up on the screen. And then it's moved a small random amount, and that's when it's shown red. Now, there's only one restriction on this movement, and that's that it absolutely has to preserve those summary statistics, okay? But it is allowed to move away from the shape, okay? So you can see I've isolated the iterations where that actually happens, where the point is moved further away from the heart. And this is necessary, again, because this is randomized, so that it helps you avoid getting stuck in local optima. But the likelihood that you make these decisions does decay over time. So over time, because you want to hopefully, I'm going to say converge in quotes, and you'll see why later, but hopefully you want to converge to the shape. And so you want to reduce the chance that you're just going in the wrong direction as you near the end of your iterations. But this does decay over the lifetime of however many iterations you're running, it's decaying over the whole process. And this is called the temperature. So simulated annealing is referring to annealing in like metalwork, and so that's where the temperature comes in. So one small change I did add to the algorithm itself was changing how the points moved over time. So I'm following a similar process, which I'll show you on the next slide, but you can see here that the points seem to slow down as they start getting towards the heart. I think that adds a nicer effect. It's like they're running away from that first shape and then they're settling in the new one. And that's actually the exact same decay. But here, you cannot fall to 0 because then that means you're just wasting compute calculating these changes and not actually moving anything, and that's not worth it. So this decays to a number here that is configurable. Okay, so now I want to share some of the limitations that are currently in this project and some areas that could be for future work. So the first I call bald spots. So you'll see, for example, ideally we would have something like this, right? Perfect heart looks just like the drawing of what the shape is supposed to be. But what actually happens is something like this. And this is dependent on the input, right? So if you can see, the dinosaur really doesn't have much close to this outer ring here. So they're all in here, so that's far movement. So they end up clumped up here or down here. And that's because there's nothing to penalize that movement. There's no repelling force in the current algorithm. But there are definitely ways to do that. I just haven't done it yet. Another thing is the morphing direction. When I initially started doing this, I had wanted to turn a drawing of a panda into a dinosaur because I'd be like, something not so scary into something super scary would be funny. But because of how the shapes of things are, you can end up with a dinosaur without a nose or something, and that just doesn't look too scary at all. And again, that's the bald spot problem coming into play. But there's also more challenges. Like in that case, you could force the points to be around the same area in the XY plane and kind of get it to work. But I was telling you before about how the shapes use the data to figure out where to place themselves. If they're both data, then how does that happen without you manually doing it, right? So that would be another issue with that. I think shape to shape is much easier because you can just have some, intermediary data set that is like in one spot and they both use it and then they do the transformation. But the bald spot probably is still a problem. Like if you think about maybe a heart to the infinity shape, right? They're very different dimension-wise, and you might not be able to fill that out. So speed, I think, is the biggest thing that would be nice to change. As I mentioned, the original algorithm is untouched. It's an iterative algorithm, so you do have that cost of going one by one. And what's worse is you pick a point, you pick a random movement, you evaluate it. Oh, actually, that doesn't preserve the summary statistics. Okay, let's try again, right? So there are a lot of wasted steps in that. So maybe it's possible to do like bulk editing or some kind of like averaging between the two shapes, right? But I haven't had a chance to do that. If someone wants to do that again, I'm happy to take a look. Okay. Another interesting thing, this is much less of a problem. So the scale of the data affects how many iterations it takes to do the transformation. So here is the actual size of the dinosaur. This takes about 50,000 iterations, and this one is half size, takes about 25,000. This one is double size, and it's 77.5 thousand. So not quite the double. I say this is less of an issue because if you have it too big, with data morph already, you can scale it down. You can turn it into this guy, and it's very fast. It looks exactly the same. The numbers are just different. But the reason that this is because you can only move small amounts. If you try to move bigger amounts, the random selections are sometimes way too big, where it's trying to move it beyond the bounds. And again, you're in that situation where you waste thousands of iterations trying to find something that you can move to. And every time it's like, nope, not good enough. And then you end up kind of getting stuck. Okay, and I hinted at this before, convergence, right? So right now, and this is also where the speed becomes painful. So when you run the algorithm, you have to specify how many iterations you want to run. So let's say you run, maybe you run this guy, okay? And you run him for 100,000 iterations, and you look at the result. He actually was at the end just dancing around the shape. Like it was already there, and you now have wasted time in the middle of the animation that you actually want to cut out. So the only way to do that is you'd have to either edit the resulting GIF, or you rerun again for 50,000. And then conversely, maybe it was like, oh, you were so close to getting to the right shape. Okay, you didn't get there. Let me rerun again, but for more iterations. And so I'd like to have something where you have some sort of early stopping criteria, some kind of convergence criteria that says, I'm able to detect that we're close enough to that target shape that we can stop now. And then obviously still have some maximum iteration, because some shape combinations simply don't work, right? If you're trying to convert something that's very tall vertically and very thin, horizontally into something that's the opposite, it's just not going to happen. Like you cannot push those points over there. It's not going to work, at least with this algorithm. Okay, so a little bit about what I learned from this whole process. So the first thing is that repeating research is hard, right? So even though you're given the paper, they tell you how they did it, and in this case, at least there was some code of what they used, but it wasn't actually complete, right? So I just set about doing, how do I convert the data source, so that dinosaur, into the circle, which was one of the examples presented in their paper. And I accessed the code, which I've linked to up here if you want to check. That is not like the initial code they had. That's the code that they put somewhere and attempted to clean up. So then you also have the traces of that where it's like, what is this function used for? It's not referenced anywhere. Or like a parameter that was clearly there at one point that's gone but documented, and it's like, what is going on here? And then a big problem was just those generic names, right? So like C, what is C? I have no idea, right? And so, yeah, so initially I wanted to turn something into the star. So imagine you see just a bunch of line segment endpoints. What are those numbers? No idea, right? So the circle is the easiest because you see some points, you see two values, and you look at the data and you're like, oh, wait, maybe that is the center of the circle and that's the radius, and then the center is probably the mean, and the other thing is maybe some multiple of standard deviation, right? So it was a lot of reverse engineering to figure out what was going on. So just getting this to work and even figuring out which packages they were using. Took me 4 hours to reproduce that, right? And then, as I mentioned, I wanted to get a different data set for this. So if you've been here for previous PyCon Portugal, I've done a workshop on pandas. And usually when I do the full version, it's about 4 hours. And so when I get to the point where I'm talking about data visualization, we've done at least 2-3 hours of data wrangling and just dealing with numbers. So to motivate that we need to use visualization, I wanted to have a nice, impactful something. And it makes sense to use a panda with pandas workshop, right? So I wanted to convert a panda into one of these shapes, right? And again, that was where it was like, what are these hard-coded values actually representing? So I found a shape for a panda, I traced it, converted it to points, and then I had to move it around a bit in space. So it kind of was like in a similar spot to the dinosaur to just see what the numbers were doing. And this, like, I didn't really even change the code. This took nearly 2 days to get that bit working, right? And then once I had that, I was eventually able to hack it enough to get the star. And I was like, wow, this is really cool. So I had that. I mean, it didn't work perfectly because it was still, it was designed for the dinosaur, right? But I was able to get it close enough. And then I got the idea that this could actually be a very good teaching tool for people to make their own things, to just understand how these concepts work. And so then I decided, why not build and distribute a package? So then I had way more challenges, right? Because at this point, I had to pay back all the technical debt from the research code. So getting rid of all those things that had seemingly no purpose, documenting things, refactoring that monolithic code base, and that's where I came up with the data sets and the shapes and how do we work on arbitrary values this way. Another interesting thing is that because I wanted to actually have documentation everywhere, I ended up building a pre-commit hook to validate NumPy style doc strings that ended up getting merged upstream and actually led to me becoming a core developer of that particular package. And a plug for tomorrow, I'm doing a workshop on pre-commit, so if you're interested in how to make your own, please come to that. And aside from that, this was a really interesting project because whenever you're contributing something in open source, so many things already exist by the time you get to that project. They already have GitHub Actions. They already have it published to PyPI and Conda Forge, right? They already have a test suite usually in place. They already have documentation built and hosted somewhere. So you never have to figure out how to do that yourself in a public space. And then similar in work, again, probably the same thing and probably different tooling, right? So I had to figure out all of that stuff on my own. And like I said, even if your package really isn't used by anyone, it's still a nice process to go through just to see those steps. And it gives you an even stronger appreciation for what people in open source do for us. Okay, so all of this, getting that working and published, took 2 months. And that was largely because I was going to go on a podcast where I had said I was going to talk about this. And so the fire was lit under me that this needs to be done by then. But if that weren't there, probably more like 4 months, 6 months. And I will say that now, I don't get much time to work on this every year. I was saying earlier that basically whenever I'm at a conference, it's the only time I get work done on these because it's like I can focus on these things. Yeah, and I also want to highlight that, especially because I was doing things that I didn't know how to do in the wild, right? Like figuring out how to host the docs or using a new Sphinx theme, for example. There were points where I was reading the documentation and it just wouldn't work for me. And I was like, why is this not working? And it's healthy to go into those situations thinking, oh, I must be doing something wrong. Let me read it again. Sometimes it is actually that they are wrong. And so I was able to fix a couple of those cases that I bump into along the way. Okay, so the slides are on my website. And so here you can take a look at these later, but some helpful resources that I used at this point to get things going. Yeah, so as we covered, right, summary statistics alone are not going to be enough to describe your data. You absolutely need to visualize, and ideally more than one visual, right? We saw when we had added just the histograms, we got a lot more information about the points versus just those scatter plots. So if you want to try out Datamorph, you can install from PyPI or Conda Forge. There's the link to the docs, the repo itself, and if you're in any kind of teaching, that's for some ideas for how to use it in the classroom. These are the papers that I referenced if you want to read those. And on the right, you have links to follow stuff I do online. And on the right, on the left, the QR code for feedback form to let me know what you thought of this talk. And thank you.